So if we go to 161, come on. So this, our outline or whatever. Oh, I called it recoupment. Oh, I gotta fix that. Recoupment. So, you have 1 week after the assignment is returned to you. So not starting today, starting when you get it back. Because the assignment will be marked by TA, teaching assistant. And after you get it back, you will have 1 week to get your feedback, to look at the feedback you got on the assignment. For an assignment like this, you're probably not going to get a lot of feedback. The feedback is going to come in the form of just like your marks, where you'll be like, oh, okay, I didn't do that right. As the assignments get more and more complex, the TA might have to give you more and more intricate, sophisticated, complex comments on what you got wrong. But you have 1 week to look at what you got, see what you did wrong, and make the correction. If you do that and submit it, there'll be a new submission link. So there's assignment 1 submission, and there'll be assignment 1 recoupment submission. If you do that, you can recoup 50% of the marks you lost. So that's assuming you make the corrections correctly. So if, for example, you got 80% on the assignment and your eligibility for recoupment is everything, and you make all the corrections correctly, you can then get 90% on the assignment at the end of the day. Cool, right? There's a catch, though. The TA has to deem, and the TA is God in this scenario. What they say is what they say. What they say goes. They will deem whether or not each part is eligible for recoupment. Meaning, if you just hand in absolute trash for part 3, let's say, you're not going to be eligible for recoupment. Okay? You had to have okay, you submitted it, yeah, okay, you did it, but you were wrong, you're eligible. They're going to err on the side of being nice, of course. But to hedge against people like, I can't get it done, so I'm just going to vomit on the computer screen and hope for the best that I can get recoupment. No, that's not. You didn't find a clever way to submit an assignment late. So at the bottom of the assignment, feedback, you will have, I should bold these. It'll be like yes or no. Part 3, eligible? Yes. Part 4, eligible? Yes. Part 5, eligible? No. And so on. But you can still get the recoupment for each part. Cool? I think so. Chances are, I don't know. You will not be eligible for recoupment if you got it perfect. So if you're like, oh no, I'm not, what did I do wrong? Nothing, you got it right, so you're not eligible. No sense doing anything, okay? But that's how it's gonna be. So you have 1 week after you get it returned to submit your updated files. Also, before you submit, make sure to read the relevant part of the syllabus to make sure you see all the rules. You have to make clear to the marker what you changed. If you just submit an updated version of the file, the TA is going to be like, but I don't know what the hell you did. I'm not going to go through, search for your old assignment, take it and compare it and see what, no, that's going to take way too long. That's not going to work. This is a nice thing for you. Don't screw it up. Cool? Cool. Yes?
Will we get a filled-in version of the spreadsheet of that?
Yeah, you will get this, yeah. So you will get, oh, okay, yeah, you got that right, you got that right, you got that right, oh, you didn't get that right, you got that right, you got that right, you got that, and then at the end, ooh, oh, that's not right, why did that not, it didn't save right, I have to update this, obviously, because these should calculate the totals, but whatever. Oh, I think it's because I moved some of the lines around. Yeah, all right, I'll figure that out later. But anyways, yes, you will get a filled-in version of this. Each of you will get your own. All right, any last questions about that? Who here thought assignment 1 really wasn't that bad? Who here thought it was okay, it's not that it wasn't that bad, but I guess it wasn't that hard. Who here thought, oh man, that was the worst thing ever? Okay. If you were struggling, come to office hours. Only like 4 unique individuals have come to office hours so far this year. We're like, what, halfway-ish through the semester? That's weird. I sit in my office all alone wondering, where are my poor students? They need help, I want to help. So come to office hours. Don't miss that option. All right? Cool. Any last questions before we get going? Yes?
For the next assignment, is there material that we haven't covered that is relevant to the assignment still?
It's a good question. I'm pretty sure we've covered everything, but list references, alias, tuple dictionary. Yeah, I think we'll have covered basically everything. If there's something missed, it's something that you can fill in the blank pretty easily. And if not, we'll hit what we were missing today. Cool? Cool. Good question. Do I have a due date for assignment 2 yet? The 31st on Halloween? Look at that. How nice. It's about zombies, right? Perfect. All right. Let's get to lists. So, I actually already showed you all of the interesting loop stuff, so I'm going to move through the rest of the topic pretty quickly. But just to re-hit the last thing, lists are mutable. With a string, I can access individual characters by indexing the string, right? But I was never able to change what was at that index within the string. With lists, I can. With lists, I can access the information from a specific index. I can say my list at index 2, right? And it would say C in that scenario. Or I can even assign things by saying, there, on line 2, another list at index 2 is now X. Great, so I can actually go in and change. So lists are mutable. You can change them, which is great. But I do want to give a bit of a warning where a lot of times the mutability feature of a list is something very critically important for what you're doing. But a lot of times, if you can make it such that your list that you're using, you treat it as if it is immutable, there's a lot of advantages to that. I won't get to those right now. We'll hit that as we go. And assignment 2 kind of walks you through that a little bit to talk about the mutability, immutability, whatever. But just as a heads up, there is some reason you might want to pretend they're immutable and just like don't change them. Because it helps protect against potential bugs and makes your code a little bit more simple. Anyways, they are mutable. Okay, lists and loops. Well, we already saw a for loop like this, right? If I have a collection, it's just a list. It's a string hello, 10, true, 100.001. For thing in collection of things, first time through the loop, what is thing going to be? Great. Next time through the loop, what is it? Then what? Then what? I'll assume that last one was correct, because all I heard was great. Awesome. There. For each thing in collection of things. That's the idea. And it's in order. You start at the beginning. And if I say, like, look, if I'm at the number 10, and I say, what comes after the number 10 in that list? What comes after? True. Why? Well, because it's there. What came before? See? It's a linear collection of information. It's a linear data structure. So, you know, there's a beginning and there's an end, and you know that there's like an order to these things. Like what comes next, what comes next, what comes next. Make sure your masks are on. So, we've also seen range, right? Range is a great way of using a loop if you need to just, like, look, I've got some number and I want to do some chunk of code n times. Range is fantastic for that. Just for I in range 5. Great. If I print out I, I'll see 0, 1, 2, 3, 4. Now, I don't need to actually make use of I in that for loop, right? I can just say for I in range 10. If I run this, it just says hi 10 times. So I don't actually care about the I in this particular scenario, but it's there if I wanted to use it. This would be similar to like a while loop, but with the while loop I need to set up this like I counter variable. I'm checking my condition, and then I'm incrementing I. They are equivalent. They are functionally equivalent, the for loop and this while loop. But you might see here that the syntax is a little simpler for the range version. Where here I've got the counter, I've got the condition that I'm checking, and I've got the I increment. Nothing wrong with it, but the for loops is perhaps just a little cleaner of some syntax for this scenario. If you don't like the for loop with the range, fine, you can do it with a while loop. Now, while loops are far more general because a while loop just loops while some condition is true. In this example, the condition is like, well, it's that counter condition. Well, the counter is still less than some value 5. Great. But while loops are more general, but the for loop, sure, it's got its specific uses, but it ends up with some nice cleaner syntax. We'll skip this one. And then, so I showed you this last time. If I told you, so this is just a linear search example here. If I said, and I did show you this example yesterday in class just with different names of functions. I'm doing a linear search for something in some collection, right? So I'm looking for a needle in a haystack. In a linear search, you know, the first one we saw was return true if it's there. If it's not there, return false. But we had that slight variation of this linear search that we saw before, where it wasn't just telling me true or false, it was tell me which index that thing is at in that collection. So if I'm looking for X in some list, and X happens to be at index 7, I want it to return 7, not just true. And then we would say, well, if it's not there, return -1. Just because -1 is a special value, that would mean, okay, if I ever get -1 back, that means I know it wasn't found. We often call those things a Sentinel value. It's a value that we know just has special meaning. So if I try to use my good old for loop, for each element in haystack, if element equals needle, when this happens, that means I now know that that thing is in the collection. It's in the list. Great, I found it. Fantastic. And now I'm supposed to return the index. And you go, uh-oh. I don't have an index. I have the element, but I don't know which index that element is at. Shoot. So one way to go about fixing this is to use range. I could just say for I in range, the length of the collection, for the length of the haystack. I could do this. I get the length of the haystack, for I in range length of the haystack, or haystack length. I now will correspond to 0, 1, 2, 3, all the way to whatever the last index in the haystack is. So I is now going to correspond to the index. So first it starts at index 0, then index 1, then index 2. And then when I check for my equality, I could say, well, if haystack at the current index I have is the thing I'm looking for, needle, then return I, because I is the index that I'm currently looking at. And if I find the thing I'm looking for at index I, it is therefore at index I, right? So the first time through the loop, I is 0. It checks, okay, is haystack at index 0 the thing I'm looking for? If it is, return I. If not, keep going. Is haystack at index 1 the thing I'm looking for? Yes or no? Index 2, index 3, index 4, so on and so on and so on. And then as soon as I find it, I'm just going to return I. If I never find it, I finish the loop and I return -1. Questions about this? So the original method, I had the elements. The second example, I didn't have the elements. I had integers that were going to correspond to the indices that I could use to get the element, right? So this is one way to fix it. But Python gives us a fancy new special keyword. Wait, what's the difference? Yeah, okay. This fancy new key, well, okay, before that I'll just show another list, A, B, C, D, E. For I in range the length of another list, so 1, 2, 3, 4, 5, I starts at 0, and we print out another list at index I. So 0, and then what is this list at index 0? A. Why? Well, because it's right there. It's the thing at the beginning. It's index 0. I is 1. The thing at index 1 is B. I is 2. The thing at index 2 is C, and so on and so on and so on. So we can see how before we kind of like cut out the middleman, right? Like, oh, don't worry about the index. Just give me each thing. Great. But sometimes you care about the index. You can't cut out that middleman. Python gives us a special thing called enumerate. Enumerate gives us the best of both worlds. It will have a loop, but enumerate, your for loop will actually have two values that are changing every time through the loop. The first one is going to be the index, and then element is going to be the thing there. So it's a combination of the two. Here I can say, well, if I print out I element, you can see I don't have to index the list. But I'm just going to show you another thing here. I'm just going to take this. If I run this, what do we see? Okay, great. But if I do, there. Look at the output and make sure this makes sense to you. It's critically important that this makes sense. If it doesn't, raise your hand and ask a question. First time through the loop, I is what? 0. What is element? Well, the first time through the loop, element will be the thing at the beginning of the list. It's A. Which is also just another list at index 0, right? Element and the thing at the current index are going to be the same. They have to be because they are the same thing. Element is just another name for this. It's just another way to get that. Any questions? So if we go back to our index of example, I can go back up here and use enumerate. I can go back up here. Enumerate the haystack. I can still check if element is equal to needle, but if it is, well, I just return the index. Oop. Index. And that would work just fine. Any last questions about this? Okay, we're about to move on to the next topic, which is always the point in the semester where be honest. Raise your hand if you feel that no one is expecting you to be an expert on everything we've learned so far up to today, right now. No one would expect that. But raise your hand if you're like, I'm following along, I'm getting it. After a little practice, I know I'll kind of, get it. Raise your hand if that feels like you. Okay. Most people in the room. For those of you that didn't raise your hand, is it because you're entirely lost or because you're like, no, I get this? All right, well, no one said anything, so I'm going to assume it's the latter because it's easier for me. We're about to move on to an exceptionally important idea. But this important idea will be where if you're like, yeah, I'm following along, this is going to be where you probably get angry. Because it's going to feel as if I threw a wrench into everything you've known so far, everything you've learned so far. It's going to feel like I've been lying to you or something. But I promise you, everything I'm about to tell you is going to be consistent with everything you have learned so far in the course. The trick is to understanding what's going on in the back of how the computer's working before you can see how everything is consistent. But as I start talking about this, there's a good chance you're going to be thinking to yourself, whoa, this is way different than everything we've seen so far. No, it's exactly the same. This idea is something called references. Now, as I talk about references, I'm going to warn you. I'm talking about references generally, kind of like classically speaking. Python, it's not going to work exactly like this in Python. It's not going to work exactly like this in other programming languages. But this right here is the high-level idea of what's going on. So if anyone in here is a Python expert and you're hearing what I'm saying and you're going to say, well, actually, I know. You don't need to tell me, I know. It's high level. So what is actually stored in our variables? This is the root of this topic. Okay, yeah, the idea is presented below, very high level, and they're not entirely correct for Python. The differences come up with nuance, sufficient to cover import, whatever. Okay. Typically, so here's another note. Typically, by convention, when referring to memory addresses in your computer, we use hexadecimal, which is just, instead of having 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we have an additional A, B, C, D, and E, and F, where F means 16, where if I just write an F, that means the number 16. No, the number 15, pardon me. For simplicity, I'm just going to pretend everything's just going to be in decimal. So again, if there's anyone in the room that's going to be like, well, actually, it's all hexadecimal, I know. Just bear with me. For simplicity, I'm just going to use decimal numbers. And if everything I just said left you going, wait, what? Ignore everything I said then, because you're already in the right state of mind. Here is an idealized view of memory. And yes, I give you permission to talk about how great my Microsoft Paint skills are. I'm just going to do it this way. Here is the idea. Ideally, our memory goes on forever. It doesn't, obviously. But it goes on forever. And I have some content in memory, but each memory has a specific address. So this is RAM. Random access memory. This is RAM. This is where we store things that the computer's currently doing. When you load up Chrome, it's loaded into RAM, right? And that's where everything's stored. When you run your Python program, all of the variables and whatnot that are currently being used for calculating stuff is stored in RAM. It's like the table, if you're working on stuff, it's the table where you're putting things down when you need to go do something else, and then you can pick them back up and whatnot. That's where it's stored. RAM is broken down into memory addresses. You can kind of think of it as a giant list. Each address has a number, typically a hexadecimal number, but here I'm just showing decimal. And I just started arbitrarily, I show index 1, 2, 4, right? It starts at index 0 and it goes to index a bajillion. But I just happen to show you memory addresses 124 through 135 here. So I have the addresses, that's like a location, or like the index of a list. And then I have the contents in memory. Okay, that would be, well, what values are in the list. So you can see the analog here with the list. This goes on forever. If at any point during this discussion you have any question about this, ask. Because it's a weird one and I want to take my time with it if people have questions. And it's really boring if I just talk at you for the full hour. Yes?
When you say it's like a list, is it like kind of like something we've seen? Is it linear?
Yes, it would be linear. It's just, there's a thing at the beginning and there's stuff that comes after and there's stuff that comes before. It's just like a list in the abstract sense.
Okay.
Yeah. Great. So this is how it looks like. Primitive types in memory. So a primitive type, which kind of isn't really a thing in Python. It is, but it's kind of not. But for the sake of talking here, we're going to call primitive types. Primitive types, if I have a single integer called x, okay, don't think of it as a variable x necessarily. I've got some arbitrary integer. Pick an integer in your head. An integer is a primitive type. A float is a primitive type. An individual character is a primitive type. But those aren't really a thing in Python. Floats, did I say floats already? Booleans, they're primitive types. Strings are not, lists are not. But we have our base level types, where everything is built on top of those. In many programming languages, integers will take up 32 bits of memory. That means 32 zeros and ones will be used to represent that integer. So if you're thinking of memory, you know, I've got these addresses, but if we kind of go down and dig a little deeper, like, well, okay, but what does memory look like physically, right? Because there's a box over there that's got the memory. What does it really look like? It's just a crap ton of transistors, and the transistors hold low voltages and high voltages. And if you get enough of them in a row, like 32, for example, it would be more than that because how transistors work. But enough of these transistors in a row, I can have my 32 bits to represent the low voltages and high voltages that are the binary numbers. So I go to my computer, I type in the number 77, and whatever that value is in binary, it gets put into the transistors holding these low voltages and high voltages with the right binary type. So I can hold 32 bits of data in zeros and ones and transistors. And so, for example, if I have that series of 32 ones and zeros, it's actually the number 709,582,100. So if you can kind of envision a bunch of transistors holding low voltages and high voltages, as far as the computer's concerned, that's the number, or that number is that series of zeros and ones. Okay? But we're not really talking about the level of zeros and ones right now. We're going to break down each chunk of memory into nice, let's say 32-bit chunks. So each memory address has like 32 bits worth of data. Okay? Because, you know, an integer is like this nice atomic size. 32 bits of data, I can hold a whole bunch of different integers, you know, a large range of possible values. I'm going to break my memory, which is just a bunch of transistors, down into a series of 32-bit memory addresses. So when we go back to that idealized view, address 135 that you see there, you see that one slot, really that one slot has 32 zeros and ones associated with it. And I can shove 32 zeros and ones in there, set the zeros and ones in there, and it'll mean something if it's an integer. Hopefully that was clear, even though it's kind of weird. I'm going to start by saying this level of detail, it's important for you to take the high level away. I'm not going to ask you on the test, how is a 32-bit number represented in your computer with transistors? Like, no. The point is, I've got memory, really just a bunch of transistors that can hold low voltages and high voltages, but I group them in chunks of 32 to make a single memory address. So here's the first chunk of 32, here's the next chunk of 32, here's the next chunk of 32, and so on and so on and so on. Cool? So, great. Since we know how much memory an integer takes up, I can put integers into nice divvied up chunks of memory. So I can take the integer 709 million and just tell it to sit right here, and it's happy. Because it fits right there. Great. Sure, we could get fancy and you say, like, well, what if you need a bigger number? Can you use 64 bits? Yeah, okay, but we'll keep it simple here, 32 bits. So, we create an integer variable called x now. And I assign it the value 17. So your computer, Python's going to tell your computer, okay, we need to like save this value. So the computer's going to go, all right, you know what? I'm going to put the value 17 in memory address 126, and I'm going to remember that the variable x will get me to that memory address. The variable x is going to get me to memory address 126. If you're wondering, well, why did the computer pick memory address 126? It's relatively arbitrary. Next time you run the program, it might be in a different memory address. You don't need to deal with that though, thank God. You just say x equals 17, and the computer does all this for you. So x is like another name for memory address 126, and at that memory address, we have the value 17. So far, so good? Yes?
Is there another memory address that has to be used to store the fact that x is at that?
There would be details like that, but let's not worry about that stuff right now. Good question, though. Okay. Now listen carefully. This is the first half of that whole like, so it works differently? No. Let's be clear on how it works. If I come along and I want to make a copy of the value stored in x, which is really stored in memory address 126. If I want to make a copy, I would come along and write something like, in my Python code, I would say something like, okay, y equals x, right? I would go and say like, okay, x equals 17, right? And then I would say y equals x, yeah, and then print x and y. They're both 17, right? So I just copied whatever was in x, which, memory address 126. So here's what Python would do. It would find another memory address. It just so happened to pick memory address 129 because. And it goes to the memory address for x, which is 126. It looks at the content in that memory address. It copies those zeros and ones and puts them in another seat right here. The same, I copied the zeros and ones, put them into here, exactly like they came from here. All right? The contents of the memory address are just simply copied. Everyone say this with me. I'm going to say the contents of the memory address are copied. Say it now. The contents of the memory address are copied. That's it. That's it. None of this, sure you learned something new, a little bit of memory addresses and whatnot, but I'm willing to bet that what I just talked about is relatively intuitive, right? It's kind of like filling a little bit of the gap about like, well, how did it work in the back end? Well, okay, that value needs to be stored somewhere. It's in memory. Great. There you go. This strategy works great because I know that integers fit nicely in these seats. If it was an individual character, it would, it takes 32 bits as well. If I wanted to copy the character, it would be great. It could copy from that seat. If it's a Boolean, really a Boolean only needs one bit, right? 0, 1, but whatever. I know it'll fit nicely in one of those addresses, one of those memory addresses. I'm happy with that. The trouble is, when I have something like a string or a list, the trouble we run into is, well, hold on. How long is that list? If I have a single integer, it fits nicely in this seat right here. There's no issue with that. But if I have a list, how big is that list? If that list has 17 integers, I can't store 17 integers in those 32 zeros and ones, right? It's not going to work. We have an issue. Let's say I have 10 characters. So if I want to store 10 integers, each one takes 32 bits. If I have 10 of them, I need 320 bits. I go to one of these memory addresses and I go, I only have 32. I can't fit 40 bits worth of information into 32 bits. It's not going to work. Why? Because that's not how our universe works. You can't do that. The screw is too big to fit in the hole. It's not going to work. So, I have a list of length 8. The contents are labeled A through H, but these are arbitrary labels. We can think of them as integers if we want. You can think of them in characters, whatever. But you can just pretend I've got a list of integers. In the example so far, everything's broken up into 32 bits. And I have 8 integers, which means I need 256 bits. But I can't fit that into 32. Great. So, here is what I would think an intuitive, simple solution. Well, okay, so if a single integer can fit in one spot, just put each integer in its own memory address. Except I'll just need to kind of remember that this chunk of memory right here is my list. So A would go here, B here, C here, D, E, F, G, H. And maybe we've got an I here for fun because there's a number. So I can fit each individual integer in its own seat. But I of course need to remember that but this chunk right here is my list. Does that seem like a reasonable solution? I think so, right? I mean, it seems like the simplest solution. I don't know how good it is, but it seems simple. I only have so much room in each address. So yeah, we section off a chunk of memory that we need, and we put each thing in there. But the problem is, the problem we have, there's a bit of an issue. So we store each element in the list in their own memory location, similar to how 17 was. And we're going to section off the block of memory to hold the list, to hold reference to each of the elements in the list. Okay, so what I do, I have my list of A through H. My computer just happens to find memory addresses 677 through 684 to put A, B, C, D, E, F, G, H. So there's my list of information. But I need to know where that list is, and I need to know a little bit of information about that list too, right? The list isn't just this data. I need to kind of know, well, where is the list, how big is the list, and all that extra stuff. So, here's my list in memory. We need to keep track of the fact that our list starts at memory address 677 and goes to 684. So, we use something called references. If I wrote this code, Z equals A, B, C, D, F, G, H, that's just my list of 8 things. Here is what would happen. Let me make sure I didn't miss something here, okay? Given the above, computer finds a block of memory to store the list. Each element fits nicely into its divvied up section. Then the information needed to find and access the list content is stored in the piece of memory labeled with the variable Z. So the information needed to find and access and details about the list stored right here in memory address 131. Why? Because the list is not stored in memory address 131. The list is stored in memory address 677 through 684 or whatever I said it was. What's stored in the memory address Z is a reference to where that list is. So now I can fit something nicely into this piece of memory. I'm going to label it Z. It can fit there nicely, but I use what's there to get me to the list I actually care about. So the contents of the memory here, unlike with the primitive type, where it just stored the value 17, The contents of memory address labeled with Z, 131, is storing a reference to where the list actually is. It says, go to memory address 677. Yes?
I would have known to stop at 684.
There would be okay, so you've asked a great question that has a lot of nuance. Classically speaking, it wouldn't. If you go to some of the older programming languages, you need to make sure you also store in variable A how long that list is. So you would know where it starts, but you don't know how long it goes, which is just a nightmare. Fortunately today we've got fancier ways of doing it. But in reality what we do is the memory address actually stores an object that stores the information about it that has another reference. It's a whole other thing. You've asked a great question that has a really nuanced answer that maybe we don't get into right now. Good question, though, nonetheless. So we are now storing a reference, not the data itself. The data itself is stored somewhere else in there, right? It's stored somewhere. But we're storing the reference. Oh yeah, and here's the activity. I've already kind of spoiled this for you, but why do we start indexing things like lists at index 0? Well, the reference says the list begins at memory address 677. And then it's offsets. The indices are offsets. So it's like go to memory address 677 and take 0 steps. Great, you're at the beginning of that list. So see at 677 I'm at A. Index 0 is A. If I take 1 step, it's B. So it's like saying the indices are kind of like just doing arithmetic. It's like saying go to memory address 677 plus 1. Index 1 is like plus 1. So that really means memory address 678, which is great, there, it's the B. Pretty cool, right? But that's why we start indexing at 0, is they're offsets. Now, here's the other half of the thing I was warning you about. And hopefully, after I finish describing this, you're going to think to yourself, I don't see where the confusion was, because maybe I made it clear enough as we were going. If we want to make a copy of Z, like we did with X and Y, maybe we would write something like W equals Z, right? Remember I said Y equals X to make the copy of it. So if I go down here and I say A equals, or no. There. And then I say W equals Z, print W and, or Z and W. We just see the list twice. A, B, C, D, E, A, B, C, D, E. Great. This is the same as like this, right? But here it's the list. However, the catch is, and it's not even a catch. When I said Y equals X, what happened? The contents of the memory address for X was copied into the contents of the memory address for Y. So when I write W equals Z, the contents of the memory address is copied to the contents of the memory address of W. The exact same thing is happening. All that's happening is the contents of the memory address of the variable you're using is copied. It's the same whether it's a primitive type or not. But remember, it's a reference. So if W gets created, it just so happens to go to memory address 134. I copy the contents of memory address 131, where Z is. And what is it? Well, it's a reference to 677, the beginning of that list. But we've got a funny thing here. How many copies of 17 are in that RAM? Yellow. Two. It's not a trick question, it's just 2. 126 and 129. How many copies of the list are in RAM?
1.
1. But we have how many references to that one list. So, let me go back here. Here. I'm just going to do y equals x. And then if I say x equals 20, print x, y. When I hit run, what will you see? Assuming I spell print right. Print. 20 and 17, exactly. The value is 17, copy the 17, change the thing at x to 20, x is 20, y is still 17. I hit run, this makes sense, right? The value in y was left alone. If I go z at index 0 equals x, and then I'm going to print after, look at the output. Where before the value of y was left alone, you might be tempted to think, uh-oh. Look, I printed out z, we see x, b, c, d, e. And then I printed out w, and I also see x, b, c, d, e. What's going on there? Because before, in the y example, the y was left alone. Why was the w altered? There's still only one list. W was not altered. W is just a reference to the beginning of that list. So when I said z at index 0, it goes, okay, memory address 677, become an x. Great. And then I print out that list, I see x, b, c, d, e, f, g, h. And then when I say print out w, it goes to that same one single list that we just altered. In this case, we have aliases. Two variables that reference the exact same thing. We'll end here.